Welcome everyone. Today we're going to learn a concept in stoichiometry known as limiting reactants. You see, the limiting reactant is the reactant that is consumed first. It limits the amount of product that is formed. In fact, after a reaction occurs, there is none left. The limiting reactant is completely consumed. Okay? So I'm going to give you an example so that we can take this in a way that is more understandable. Imagine if you have 10 burger patties. And I'm going to use this example to illustrate the point of a limiting reactant. And let's say I had 50 burger buns. So if you look here, these are my two reactants, and what I'm going to do is I'm going to use these to make a product. My product is a hamburger. So the question is, based on the amount of reactants that I have, how many hamburgers can I make? Think about that. Now, you should have answered 10 hamburgers. I can only make 10 hamburgers, and the reason for this is because I have a reactant that limits how many burgers I can make, and that is the patties. You see, if I had more patties, I can make more hamburgers because I have extra buns. Assume that we have 2 buns per patty. So after I make the 10 hamburgers, I have no patties left. That is the definition of a limiting reactant. However, I'm going to have some buns left after the burgers are done. That is known as the excess reactant. You see, if you think about it, I'm going to need 20 buns to make the 10 burgers. I have 50 buns available, so when the reaction is over, I'm going to have 30 buns that did not get used. So these are the excess amount. So when reactions take place, one of them determines how much product is made, and that's known as the limiting reactant, while the other one is found in excess, and there is usually some left over unreacted. So let's put this into mathematical practice. We can do a limiting reactant problem in terms of mole to mole or mass to mass. Now, the more common one that you'll see is mass to mass. However, I'm going to start simple, and I'm going to show you an example of the concept of limiting reactant using a mole to mole problem. If you look at this equation, it's already balanced. It says that you have 0.552 moles of aluminum, and it's reacting with 0.887 moles of chlorine. They want to know who's the limiting reactant. Is it aluminum? Is it chlorine? And what is called the theoretical yield of aluminum chloride. So they want the answer in moles. So notice what we're looking for is aluminum chloride. So we're going to call this B like we normally do, the unknown. This is also known as the theoretical yield because when we do the math now, the answer will tell us how much aluminum chloride we can make. So this is the equivalent of how many hamburgers we can make. Now, notice there are 2 givens. In a limiting reactant problem, the 2 givens will always be the 2 reactants. Remember that we use the letter A to represent the given. So, since we have 2 givens, let's call this one A1, and let's call this one A2. And here's what we're going to do. We're going to do 2 mass to mass problems. 2 mole to mole problems, okay? Because these are mole to mole, so this makes it a little easier. First, we're going to compare aluminum to aluminum chloride. In other words, A1 to B. So we're going to use A1, which is aluminum. And according to when we do mole to mole problems, you get the moles of the given, in this case A1 or aluminum. Then you multiply by the mole ratio, which B over A1 is 2 over 2. Now, when you do the math, the number doesn't change. So we stay with 0.552 moles, but it's now moles of B. B happens to be aluminum chloride. Now, we're going to put a little box here. This may or may not be the final answer. We have to do a second mole-to-mole, so this time we're going to use the other reactant called A2, or chlorine. And according to the question, we have 0.887 moles of chlorine. The new mole ratio between B and A2 is 2/3, so you're going to multiply by 2, then divide by 3, and you get 0.591 moles of B. Now here's where it gets interesting. I have two answers. First, I did A1 to B and got 0.552 moles. Then I did a second mole-to-mole and I got 0.887 times 2/3, giving you 0.591 moles. I have two answers. Here's what you do. Compare the answers. Whichever one is the lower of the two, that is the correct answer. What are we going to do with this one? You're going to throw that answer out. That answer is useless. It has nothing to do with the problem. The lower answer is the real answer. That's the equivalent of how many hamburgers you're going to make. This is known as the theoretical yield. Okay? So the theoretical yield is you're going to make 0.552 moles of aluminum chloride. Now, there's another question we want to answer. Which reactant gave us the lower answer? Was it when we used aluminum, which is A1, or was it when we used chlorine? Well, we got the lower answer when we used aluminum. So, aluminum is the limiting reactant. This would be the equivalent of the burger patties. And chlorine is going to be the excess reactant. This is the equivalent of the buns. In other words, there's going to be chlorine left over after this reaction occurs. This is how you do a simple mole-to-mole limiting reaction problem. Here is it's worked out here for you. Here's a sample so you can preview. Notice they did it twice. Here's A1, here's A2. Here are the two answers that they got. Notice how they throw out the higher one, they keep the lower one. So that theoretical yield is highlighted in yellow, and the limiting reactant is highlighted in blue. There are two separate answers here. Now, let's try this. Skill Builder 8.4. I want you to try this one. It's another mole-to-mole sample, and I want you to find the theoretical yield as well as the limiting and excess reactant for this problem. Pause the video, and then when you're ready, we'll work it out together. Okay, so I'm assuming you did this, and if you look here, the problem says we have 4.8 moles of sodium, so let's put it here 4.8, and it's moles. We got 2.6 moles of fluorine. Notice we have two givens. They want the limiting reactant and theoretical yield of NaF, sodium fluoride, and they want it in moles. So this is our B. We're looking for the theoretical yield of this guy here. So we have two givens. We'll call this one A1. We'll call fluorine A2. And we're going to perform two separate mole-to-mole problems. First, we'll use A1 or sodium. According to this, we got 4.8 moles of sodium, which is Na, which is A1. The mole ratio is 2/2. So we got the same answer here, but it's no longer moles of A, it's now moles of NaF. Let's put a little box around that. That may or may not be our answer. We got to do a second mole-to-mole problem. This time we're going to use A2, which is fluorine, and according to this, we got 2.6 moles of fluorine. The new mole ratio is 2/1, so when you multiply that by 2, you get 5.2 moles of NaF. Well, here we are. Two answers. Compare them. The higher one you throw out. The lower of the two is going to be your theoretical yield. That is how much NaF, sodium fluoride, we will make. Now, who gave us this answer? In other words, who is the limiting reactant? Well, sodium is going to be the limiting reactant. The one that gave us the higher answer was fluorine, and fluorine will be the excess reactant in this problem. Okay? Now, these were 2 samples using mole to mole, what you're probably going to see is a limiting reaction problem using mass to mass. And if you look here, we're going to do the same thing, except now we're going to perform 2 mass to mass problems. As you can see, they have here ammonia is being made here when NO and hydrogen gas are reacting. They want to know what is the maximum amount of ammonia in grams. So this is the one you're going to label B. And they want grams. Okay? So technically, when we solve for this, we're looking for the theoretical yield of ammonia. And notice the 2 givens. They're giving you 45.8 grams of NO, and you got 12.4 grams of H2. We're going to label this A1 and A2, and we're going to perform 2 mass-to-mass problems. Now, these are a little bit more complicated. The first thing we got to do is we got to change grams to moles. Now, remember what I've said many times. Never use coefficients to find molar mass. So NO, we'll do this up here. N is simply 14.01. There's one N. O is 16. Add that up, and you get 30.01 as your molar mass. So in step 1, which is A1, we're going to change the 45.8 grams into moles by dividing by the molar mass of NO. That's going to give us 1.526 moles of A, which is NO. Once you change to moles, the next step is the mole ratio. In this case, the mole ratio B over A is 2 over 2. So the number stays the same, 1.526, and it'll be moles of B, which is NH3. Now, what we're going to have to do is we're going to have to find the molar mass of B. Okay? So let me give myself some space. I'm going to go ahead and erase this here. And I'm going to write here, let's find NH3. We got 1 N, 3 of these. N is 14.01, which stays the same. Hydrogen is 1.01. And when we add this up, the molar mass is 17.04 grams per mole. So the last step is to multiply by the molar mass. Notice I did not use the coefficient in front of the NH3. You never do when finding molar mass. And when we multiply and round, I'm going to round this to 3 significant digits, I end up getting 26.0 grams of NH3. Now let's put a box here. We're going to need to do another mass to mass. We're going to need to do A2 now. So we need to change the 12.4 grams of hydrogen and divide it by the molar mass of hydrogen. That's 2 times 1.01. which is 2.02. So we're going to divide by 2.02 grams per mole. So we can convert grams of hydrogen into moles, and you get 6.1386 moles of hydrogen. Now, our new mole ratio is going to be B over A2, and that's going to be 2 over 5. So you multiply by 2, then divide by 5, and you get 2.4554 moles of NH3. Now, the beauty is it's the same B as the previous problem, okay? Now, since it's a mass to mass, I'm going to go ahead and multiply by the molar mass of B. And when you do this and round it to 3 significant digits, you get 41.8 grams of NH3. Now, notice we have 2 answers. 26.0 when you did A1 to B, and 41.8 grams when you did the other reactant, A2 to B. Again, what you're going to do is you're going to throw out the higher answer, and the lower one, which is 26.0, that's going to be the theoretical yield. That's how many grams of ammonia you're going to make. Now, in this problem, the limiting reactant is going to be NO, because that's the one that gave us the 26.0 grams. So we're going to label the limiting reactant over here. That's NO. And that will make hydrogen the excess reactant. So we answered both questions in this problem. If you take a look here, this one is worked out for you. Notice here they're doing A1, here they're doing A2. They're converting grams to moles. There's the mole ratio. Then they're multiplying by the molar mass of B. Okay, and the second one, the same thing. They're converting grams to moles. There's the mole ratio. Then they're multiplying by the molar mass of B. Okay, on this next page, here is the math worked out for you. They're using dimensional analysis. Here are the two answers that we got. Notice, again, this is with A1, this is with A2. The lower one is highlighted in yellow. That is the theoretical yield. And in blue, they are labeling who is the limiting reactant in this problem. So here I have a skill builder for you. This one's already balanced. I would like you guys to try this. It's another limiting reaction problem. You'll notice it's a mass to mass. Go ahead, set this up, work it out. Pause the video, and then when we come back, we'll do this one together. Okay, so I'm assuming you finished the problem. Now, you look here. According to this, they want to know the maximum amount of ammonia in grams. So this is what we're looking for. By the way, since that's who we're looking for, that'll be the theoretical yield. Now, if you look carefully, it says we have 8.42 grams of hydrogen. We'll call that A1. And we have 25.2 grams of nitrogen. We'll call that A2. We're going to need to do two mass-to-mass problems. So let's start with A1. First, we got to convert the grams of hydrogen, 8.42 grams, into moles. Now remember, hydrogen, the molar mass is 2.02, so we're going to divide by 2.02, and the units here are grams per mole, and you're going to get 4.1683, and that's moles of H2. The mole ratio, B over A1, is 2 over 3, and that's going to give us 2.7789, and that's moles of NH3. Now, if you recall, we had done NH3 in the previous problem. The molar mass of NH3 is 17.04 grams per mole, so the last step is to multiply by 17.04 grams per mole, and we're going to round this to 3 significant digits. I end up getting 47.4 grams of NH3. So we'll put a little box. So this is what I got when I did the first mass-to-mass problem. Let's do the second one, A2. Here we got to get 25.2 grams. Now the molar mass of N2 is 14.01 times 2. Okay, and that's going to give us, I'll write it down here, that's going to be 28.02 grams per mole. So my first step is to change grams of nitrogen into moles. I get 0.89936 moles of A2, which is nitrogen. The new mole ratio, B over A2, is 2 over 1, so I end up getting 1.7987 moles of NH3. So I'm going to go ahead and multiply, because the last step is to change grams, moles to grams. So we're going to multiply by 17.04 because it's the same unknown, it's the same B. And this time I get 30.7 grams of NH3. Put a little box around this. And you could already tell when you get to moles that the lower one is this one. But since we had to do mass to mass because they want the theoretical yield in grams, I completed it and got 47.4 with the first reactant and 30.7 with the second reactant. Again, you're going to compare the higher one you throw out. The lower one is the one you keep. So our theoretical yield will be 30.7 grams of NH3. Now, the reactant that gave us the lower one was nitrogen this time. So in this problem, nitrogen is acting as the limiting reactant, and that makes hydrogen in this problem the excess reactant. Okay? Quick summary. So when you're doing these limiting reaction problems, obviously check the equation, make sure it's balanced. Once it's balanced, if it's mole to mole, you can proceed in one step. You're going to have to do it twice and then choose the lower of the two answers. If it's a mass to mass problem, label it as A1 and A2, convert to moles like you normally do, multiply by the mole ratio, get to moles of B, okay? And you're going to need to do this twice. You're going to end up doing two mass to mass problems. And once you do that, compare the two answers. The lower one is going to be the one you're going to keep. The lower one is known as the theoretical yield. The higher answer you throw out, and the reactant that gave you the lower answer, that reactant will be your limiting reactant. The other reactant by default will be the excess. So these problems take a little bit of practice, and the most common limiting reaction problems are mass to mass, but occasionally you might get a mole to mole, and that one obviously is less steps, so it's a little easier to do. Okay, so hopefully you could practice and get better at doing these limiting reaction problems.